Last but not least, I'd like to introduce Niki Kittur. He is an assistant professor and the Cooper Siegel Chair at the Human-Computer Interaction Institute at Carnegie Mellon. His research is on crowd-augmented cognition, and he looks at how we can augment the human intellect using crowds and computation. And so today he's going to be talking to us about collaborative cognition, augmenting thinking with crowds and computation.
Thank you, Anita. And I'd like to add my thanks, too, to the organizers for such a varied and inspiring conference. And I think one theme we've seen today is people passing on what they know to each other. And so it could be through influence, like what Emily was talking about. It could be through kind of knowing what other people know, like what Betsy and Linda have been talking about. If I was one of Stephen's aunts, I wanted you to know something, I might just pick you up and kind of take you over there, right? And so my riff on this theme is, can we build on what each other know? And this is what I call collaborative cognition. And as individuals, we have more information now at our fingertips than ever before. So with more than 50 billion web pages, an average person would need 600,000 decades to read through the internet, at which point you'd be very behind in terms of tree octopus stories. And our inability to make sense of this amount of information has significant consequences. So some have attributed the financial collapse to Wall Street institutions using borrowed money to bet on financial products so complex that to this day, few people understand how they work or what the consequences of their imploding value will be. In innovation, the US Patent Office is suffering from information overload, resulting in frustrated applicants, overburdened patent examiners, and reduced patent quality. And billions of dollars are changing hands because of questionable patent claims today. Close to home for us academics, we're seeing this in science as well. This is actually a quote from NIH, who've recognized that as partly a reflection of the complex scientific environments that researchers grapple with, the additional time it takes to train a scientist is one key issue that must be addressed. And just some stats to back this up, the age of the first major NIH grant that a researcher receives has risen from 37 to 42, and first appointment as an assistant professor from 34 to 39. And we see this in our everyday lives as well, as we try to make sense of health discussions, what products we should buy, where we should go, who should you vote for. And about a third of the time that we spend online is actually spent on complex sense-making tasks like this. So the big problem that I'm interested in that's common to all of these examples is we're taking overwhelming amounts of data and we're trying to turn them into useful mental models, okay, and mental schemas. And by mental schema, I mean a structured mental representation that's of an information space that's useful for our goals. So for example, a graduate student who's trying to learn a new field might want to know, what are the different arguments in this field? For someone who's trying to to buy a new camera, they might want to understand what's the landscape of digital cameras look like, and how do those cameras relate to each other? And this is actually very difficult for us to do, partly because we're limited as individuals in terms of our cognition. So we're fundamentally limited in terms of things like the speed at which we can process information, how much attention we have, how much memory we have, and time, right? We don't live forever. So the question that I'm going to talk about a little bit today is, how do we scale up our thinking? And I think one promising approach that's become possible recently because of the internet and technology is what I call collaborative cognition. So the idea that we can build on the cognitive processing that other people have done before us rather than having to start from scratch every time. So the idea is that, can we create a virtuous cycle in which the processing that I do can help you to process more deeply and faster, and then that processing can help someone else in turn? And I'm going to talk about 3 different examples which embody 3 different challenges for collaborative cognition. And a central thesis in all of these is the importance of structure and schemas in collaborative cognition. So the first is how to scale contributors. And I'm going to talk about Wikipedia here, because Wikipedia's had over 30 million contributors. It's one of the great success stories of collaborative cognition. It's had, these contributors have produced over 4 million articles in 250 languages. And Wikipedia touches about 15% of all internet users every day. So somehow Wikipedia takes this very complex interdependent task where people are interacting with each other and has many people working on small pieces of it while building on each other's work, right? So how does this work? There must be some catch to this. And in fact, there are quite a few catches. Think about if you have thousands of people with different points of view, how do you aggregate them? So we did a study looking at this. And before this, there had been quite a bit of work showing that the more editors and the more edits you had, the higher the quality of the article. So let's see if I can get my pointer out here. So what this graph is showing is actually featured articles, so the highest level of articles for a given level of page rank or popularity have more editors than regular articles, and that's true for the number of edits they have as well. So the idea is that if Wikipedia worked kind of like evolution, with each edit improving the article a little bit, say through fixing a spelling mistake or a turn of phrase, then we might see a pattern like this. But as we know, and some people have talked about already today, adding more contributors when they're interacting and building on each other might not always be a good thing, as anyone who's been in a meeting knows. So adding more people may add more improvements, but they can also increase coordination costs. So in a meeting, things may take a little bit longer, and a lot of times less gets done, not more. So to look at this, we took a set of about 150,000 articles in Wikipedia. And the nice thing about these articles in Wikipedia is that the Wikipedians themselves assess the quality of these articles over time. So we can take the starting age and the starting quality of an article and look at what happens when people work on it and the characteristics of those people. How many people work on it? Are those people talking to each other or not? Are they concentrated so there's a few leaders kind of directing everyone, or is the work spread out across multiple people? And then we can see whether the article changed over that period of time in terms of its quality. And when we do that, we find a pretty interesting result, which is that all else being equal, adding more people to an article does not on its own increase its quality. And in fact, it trends towards actually hurting quality. So what seems to help instead, what seems necessary if you want to have more people add more quality, is you need to use some type of coordination. And we looked at, in particular, we looked at one method that worked especially well was concentration. So the idea here is that if you concentrate the effort in a leader who can provide a structure to the rest of the article for the less engaged editors to contribute effectively, then what you see is that more people leads to a higher quality article. Whereas if you don't have that leader and you don't have that structure, adding more people actually reduces the quality of your article. Okay, so the takeaway here is that for complex collective intelligence tasks where people are building on each other's work and interacting, providing a structure or schema seems to be critical to harnessing the power of the crowd. Just adding more people won't help. Okay, so now I'm going to talk a little about scaling content. So Wikipedia is a great start at using crowds to help us turn overwhelming data into useful mental schemas. And there have been some estimates that about 100 million hours have been spent developing Wikipedia. Now, that's actually dwarfed by the amount of work that we spend every day trying to make sense of things online. So web browsing estimates are that we spend about 200 billion hours in the US alone per year, and about a third of that are spent on these complex sense-making tasks that I was talking about earlier. Just to kind of take an example, let's just say that you were moving to Boston, right? So you might want to learn a lot about what Boston is like. What are the different neighborhoods? What are their characteristics? What's the food like? What's the safety, walkability? Where are they in relation to each other and to your work? What is parking like? I might not have even thought about parking as something I should consider if I'm moving from a city that doesn't have kind of such congestion and stress for space that Boston does. And when you get this information, you have to evaluate whether you're going to trust it. Is the person who's writing this a shill for the parking company? Or are they kind of giving you some false information to move you in and inflate home prices, right? So, and do they have similar goals to you? So there are all these cognitive judgments that we're making all the time, and essentially all of that is lost because no one benefits from it. So one question is, how can we capture the work that we're doing as we make sense of information online and make it useful for others coming after us? And a key reframing here is that instead of viewing search as a problem of finding specific pieces of information, we view it as a form of schema induction. So as a way of transitioning people's mental models from kind of shallow novice representations to deeper expert representations by leveraging what other people have done before you. Now, a big problem with this, as you've probably thought of already, is that people's goals are very different, and their expertise can be very different from each other. So for example, if I wanted to learn how to plant a garden in San Francisco, I would use very different plants than I would use here in Boston, where we have things like snow and winter. And in the extreme, there may be too little similarity to make it worthwhile to look at this other person's schema and make use of it. So to examine this question, we did a series of experiments in which we would give people some tasks to research, so things like starting a vegetable garden, planning a trip, a kitchen remodel. And what we would do is give what they did to someone coming after them and see what happened. So to give you a sense of what this looked like, we had one case in which we had physical paper that we would give to people. These are clips we printed out from the web. And you can see how people would organize these, annotate them, and we would then give this to kind of another person who would come in and try to use what that person had done for themselves. And you can start to see how this is actually the second person who's reorganizing what the first person did. And you start to see some structure emerge here in terms of columns and rows and how they're organizing this information. We also did this digitally. So here is an example of one from the kitchen remodel. So iterate 1 is the first instance where someone created this. And then you can see through the second, third, and fourth iteration that more and more structure is emerging. OK, so what I'm going to show you here are the results of taking those maps and giving them to someone else. OK, so what we have are three different conditions. Solo is where the person is creating the map themselves. Iterate 1 is where they start from one other person's map. And iterate 4 is when they start from this map that is being iterated on by multiple other people. And we have quality on the y-axis. And what we find is that for iterate 4, when you start with a number of other people's iterated maps, you actually have a higher quality resulting artifact than, and better knowledge than if you had started from scratch. But we see this interesting pattern that if you start from one other person's map, it's actually worse than starting from scratch. Okay, so we see this hump, this sort of paradox about multiply iterated maps are better than one map, which is actually worse than starting from scratch. So why is this happening? So we looked into this in more detail. We asked people what did they find helpful or unhelpful about these maps. And interestingly, what people cited as the most helpful was not the content of the maps, it's the organization of the maps. And conversely, what they found the most unhelpful was the content of the maps and not the organization. So here's a quote from someone who said, although I deleted 50% of what was on the other knowledge map, it gave me some ideas right away on where to look and what factors or questions I should consider during my search. So let's go back to the example of learning how to plant a garden in San Francisco versus Boston. you might not use the same plants, but you might start to learn about things like soil acidity or temperature zones, which would apply no matter where you are. And so what we find is that the more people that iterate on a map, the more these high-level schemas start to emerge. And those higher-level schemas are more generalizable across people and more useful to them than the actual content itself. So what we're trying to do is to take the first steps towards what we're thinking of as a new kind of web. So I like to imagine this as sort of a knowledge accelerator, where the schemas of the people coming before you can help you to learn a new domain faster and more deeply. And then your learning, in turn, helps those who are coming after you. And by doing this, we are aiming to change the tipping point of the web from increasing fragmentation to increasing synthesis. And so we're right now starting to build tools to scale this process up to hundreds or thousands or more of people and aggregating their schemas and letting them build on each other. Okay, so far we've been looking at scaling in terms of the quantity of contributors and the quantity of content. And now I'm going to talk about scaling in terms of the richness of the work that we can enable. So specifically, how can we move beyond the previous examples of Wikipedia and online search, where we're taking knowledge that already exists and consolidating it, and instead think about how can we use collaborative cognition to create new knowledge? And here's one example. So this is a rake. It has a movable slider that allows you to detach leaves that get stuck on it. And this was submitted as an idea to Quirky.com, which the logo is in the bottom right. And so this is a really cool company which has crowds submit ideas for new inventions. And crowds also are involved in the process of vetting those inventions, suggesting things like what price should we sell this for, what color scheme should it have, how do we improve it, and then Quirky manufactures those products and shares some of the profits back with not only the idea creator, but the crowd that helped to improve that idea. Now, Quirky has had over 300,000 ideas submitted to it. Only 300 or so have been produced. So you can see that this is not a super efficient process. The hit rate is less than 1 in 1,000. And so about 999 of those 1,000 ideas are not currently providing much value to either Quirky or the people who submitted them. But there are a lot of interesting kernels of ideas that might help people inspire new ideas in other domains, right? So our idea here is how can we improve the idea generation process by more effectively taking advantage of existing examples using the crowd. Now, having more examples might help inspire new ideas, but examples can also stifle creativity, leading to conformity effects, homogeneous ideas. So how can we get the benefits of these examples, but without the problems of conformity? And as you might guess, we're going to turn back to using schemas. So here's actually a very famous example from the cognitive psychology literature on analogy. So let's say that I gave you a problem like there's a general who needs to storm a castle, but there are only these tiny roads that go in to the castle. How can he send his forces there? And so I might tell you the answer. You can guess the answer, which is you split up all the forces and you have them all converge to the same exact place at the same time, and you can you can storm the castle. Now, I'll give you another example, which is that here are some brain surgeons who have some gamma rays, and they want to zap a tumor, but you don't want to zap all of the sensitive brain tissue that's in between. So how could you solve that problem? If we apply the convergence schema that I showed you before, you might think of, let's take a bunch of beams that are lower intensity and have them converge at the same place at the same time on the tumor and zap only the tumor while leaving the intervening tissue healthy and alive. So we're going to take this idea of abstracting out a schema and applying it to a new domain and use that to think about a distributed process of creativity across crowd workers, and in this case, actually Mechanical Turk workers. And let me define that process and give you an intuition of that process at the same time here through an example. So here's that rake that I showed you, right? The one that you can get the leaves off of. And we'll try to do some audience participation here. I know that's a dangerous thing, especially when the cameras are on, but please overcome your natural tendencies. So here's one product, it's a rake. Here's another product, this is a skewer. So like if you want to barbecue something, you can get the meat off of your skewer by pushing it off of there. And so what common pattern do those two share? So yeah, so a slide kind of pusher thing. So you might say something like, they detach two objects by using a movable slider, okay? So now think to yourself, I'll give you a minute, what other situations might you need to detach two objects from each other? Okay, so I'll give you a minute to think about that. Children, what else do we have?
Lego bricks.
What's that?
Lego bricks.
Lego bricks, okay, all right. I'm stuck to the floor, excellent, okay. So now, can you solve your problem using a movable slider? So anyone have a? Children, okay.
Yes, I stand in between them and push them apart.
Okay, all right, so we have our children pusher, which is emerge. That's excellent. I was actually trying to think about the sailfish and the sardines the sailfish's approach to getting the sardines by kind of hitting them until one of them finally fell over. And Liz actually brought up the idea of her children, getting her children while they're brushing their teeth and trying to grab one of them. And I thought the mechanism wouldn't work very well in that case of beating the sardines until they stop moving. But sorry, that was a strange digression. So it turns out that Quirky has actually solved this problem, and here's another example of using that schema for another situation. So this is actually something you clip onto your knife to movably slide off garlic and other things that accumulate on it. Okay, so we take that process, which has some nice properties, like we can actually distribute these different parts to different people, and we can prune and direct these at different stages. And so we went to a bunch of Mechanical Turk workers, and we showed them 3 ideas, 3 different products, and we either just gave them the products, we gave them the schemas that talked about how these were similar, or we gave them both. And we asked them to do the same process that we just did here. To measure quality, we use novelty, usefulness, and practicality to manufacture, which is a common way of measuring kind of the creative process in the literature. And so here I'm going to show you the results. So here's what we get if we just give people the examples, or even if we tell people to use those examples specifically to generate new ideas. And here's what we get if we use schemas plus the examples, or even just giving them the schemas. And so you can see that people come up with significantly more creative ideas if they use schemas than if they don't. Just to give you a sense of some of the ideas they came up with, here's one which is an idea called lens cap leaves, where it was actually inspired by this strainer and using that to have a retractable lens cap, which I thought was kind of an interesting idea. Okay, so where we're going with this is we hope to take this idea forward, and again, thinking of a process of acceleration, where once you come up with a schema for an idea, oh, maybe that'll spark another idea over in a different domain. Maybe a different schema you could generate for that idea, and that will spark something else. So the idea is that we could have this process where ideas and schemas build on each other, and eventually we want to support a process of analogical search. So if you have a problem, can you search for solutions in other domains, not by surface features or by domain, but instead by the deep structure of that problem? Or if you have a solution, can you search for a problem that's from a different domain? Okay, so I've introduced a problem of turning overwhelming data into useful mental schemas, and one promising approach, which is collaborative cognition, building on each other's mental schemas rather than starting from scratch. And I want to end by saying thanks to my students and collaborators whose thinking I've been building on, and that I would love to build on your thinking in terms of how can we make large-scale collaborative cognition possible. Thank you.